Welcome. I'm absolutely thrilled that you have joined this course because today we begin one of the most fascinating journey in all of the sciences, organic chemistry. Now, I have what some of you might be thinking. Organic chemistry is hard, but let me promise you something. By the end of this course, you will not just understand organic chemistry, you will love it. This is a complete graduation level course designed specifically for b.sc and m.sc students, whether you are preparing for your university exams, GATE, CSIR NET, or JAM. This course covers everything you need. We have 12 chapters and approximately few hours of content, and we will go through everything from the very basic carbon bonding all the way up to spectroscopy, named reactions, polymers, and biomolecules. Here is your roadmap for the course. 12 sections, each carefully designed to build on the previous one. We start with the foundation and progressively go deeper. Let me give you a quick overview. We begin with introduction and carbon chemistry, then move to IUPAC nomenclature, stereochemistry, one of the most important topic in the chemistry section. Then we'll be talking about one of the most important topics, that's the reaction mechanisms, hydrocarbons, aromatic chemistry, functional groups, that too in two parts, named reactions, spectroscopy, polymers, biomolecules, and finally an exam strategy session. So grab your notebooks, draw along with me, and let's dive in. Chapter 1, Introduction and Carbon Chemistry. What is organic chemistry? Let's begin with the most fundamental question: what exactly is organic chemistry? Organic chemistry is the study of carbon containing compounds, their structure, their properties, how they are composed, how they react with each other, how we have synthesized new ones in the laboratory. Now, you might wonder why carbon. We'll answer that in just a few moments, but first appreciate this. There are over 10 million known organic compounds, 10 million, and the chemists are discovering and creating new ones every single day. No other element, not oxygen, not nitrogen, not iron, comes close to this diversity. Organic chemistry is absolutely central to life itself. Every protein in your body, your DNA, the carbohydrates you eat, the lipids in your cell membrane, all organic compounds, and it drives some of the world's most important industries: pharmaceuticals, polymers, plastics, agrochemicals, dyes, fragrance. When you take a medicine, wear a polyester shirt, or smell a perfume, that's organic chemistry at work. One more thing before we move on. Many of you may have heard the term vitalism. In the early days, scientists believed that organic compounds could only be made by living things, by some mystical life force. That theory was completely shattered in 1828 when a German chemist named Friedrich Wöhler synthesized urea, a compound found in urea, from ammonium cyanate, a completely non-living source. That experiment changed chemistry forever, and Wohler is rightly called the father of organic chemistry. Remember this: organic chemistry is often called the chemistry of life. And by the end of this course, you'll understand exactly why. So let's start with the topic: why is carbon special? Now let's talk about the star of our entire course, carbon. Why is carbon so special that an entire branch of chemistry is dedicated to it? First, tetravalency. Carbon has 4 valence electrons and it can form 4 bonds. 4, that's maximum bonding versatility in organic molecules. It can bond with other carbons, with hydrogen, with oxygen, with nitrogen. The combinations are endless. And second reason is catenation. This is unique property where carbon can bond with other carbons to form long chains, branch structures, and rings. This is the reason we have simple molecules like methane with just one carbon, but also complex molecules like cholesterol with 27 carbons or DNA with millions. Third, carbon is small in size. This allows excellent orbital overlaps when forming bonds, which means the bonds are very strong and stable. The carbon carbon single bond energy is about 347 kilojoules per mole, very stable. And carbon can form single bond, double bond, triple bond, giving us sigma bonds, pi bonds, and all the richness of organic reactivity. Finally, carbon has multiple allotropes, diamond, hardest natural substance, graphite, used in pencils, fluorines, and graphene, material of the future. Same element, completely different properties. Remarkable. Types of carbon bonds. Let's now look at three types of bonds carbon forms. And one special aromatic bond, the single bond, carbon carbon, consists of only one sigma bond. Sigma bonds allow free rotation around the bond axis, which is why long carbon chains are flexible. Bond length is 1.54 Armstrong. Energy is 347 kilojoule per moles. The double bond. Carbon double bond carbon has one sigma and one pi bond. The pi bond restricts rotations. You cannot freely rotate around a double bond. That's why we get geometric isomers, which we'll cover in details in chapter 3. Bond length shrinks to 1.34 Armstrongs and bond energy increases to 614 kilojoule per mole. The triple bond carbon has one sigma and two pi bonds. Absolutely no rotation. Bond length is just 1.20 Armstrong, very short and very strong at 839 kilojoule per mole. Triple bond makes molecule linear, and then there's the aromatic bond. As in benzene, here the pi electrons are completely delocalized over the ring. This gives benzene exceptional stability. The bond length 1.40 Armstrong is intermediate between single and double. The delocalization is what makes aromatic compound so uniquely stable. The next topic is hybridization of carbon. Hybridization is the concept that explains the geometry of molecules by mixing atomic orbitals to form new equivalent hybrid orbitals. It's fundamental to everything in organic chemistry. So let's master it right now. sp3 hybridization. The first one is sp3 hybridization. Carbon mixes one 2s orbital with three 2p orbitals to form four equivalent sp3 orbitals. The geometry is tetrahedral with bond angles of 109.5 degree. Think of methane. The simplest example, ethane, cyclohexane, all saturated compound sp3. All four bonds point towards the corners of a tetrahedron. sp2 hybridization. sp2 hybridization. In this, carbon mixes one 2s with two 2p orbitals, forming three sp2 orbitals. The fourth p orbital remains unhybridized and it participates in pi bonding. Geometry is trigonal, planar, and Bond angles are 120 degrees. Example ethylene with carbon double bond carbon, benzene, and importantly carbocations and carbonyl groups. sp hybridization. One 2s mixes with one 2p orbital, giving the 2sp orbital, pointing in opposite directions 180-degree apart. Geometry is linear. The remaining 2p orbitals form 2pi bonds. This is why alkynes are linear, also seen in nitriles and carbon dioxide. The more s character in a hybrid orbital, the shorter and stronger the bond, the more acidic the attached hydrogen. So sp carbon hydrogen bond in alkynes are the most acidic among CH bonds. pK around 25. We'll use this later when we study Grignard reagent reactions and acetylide chemistry.